Friday, tomorrow, is the last day to drop with the W. So I'll see what I can do. If you want to take a look at your multiple choice, but I need to finish up chapter 9 today, and then we're going to get into 10. Actually, 10 and 11 are what experiments 8 and 9 revolve around. Material there. And so we'll be looking at 10 and 11 together, pretty much. So if there are no questions, then we're just going to continue with 9. Where did we leave off? Maybe with 8.
Yeah, we did like electron configuration.
Okay.
For like chromium and copper.
Let's do the half-filled, the stability of the half-filled, and the filled D subshell. All right, the last part of chapter 8 just looks at electron configuration in the periodic table. The periodic table was determined using quantum mechanics. You know? Is the periodic table determined using quantum mechanics? We just have to look at the timeline. Usually, who's given credit for the periodic table? Like a number of people helped develop the periodic table, but normally there's one name associated with the periodic table. You know who that is? And this is the basic organization of it. When you organize it into shells, the first shell, or the first period, the second shell, second period, third shell. Then there's the F subshells down here. Those belong into a shell. It would just get too long during the F's in there. And so those are split off. But they would belong to that sixth shell and the seventh shell here. Sixth and the seventh shell. So it's organized based on these orbitals, filling one electron at a time. S orbital can hold 2 electrons max. P orbital can hold 6 electrons max in 3 orbitals. And the D's can hold a total of 10. The F's can hold a total of 14. But the periodic table wasn't generated from the Schrodinger equation in quantum mechanics. The periodic table was originally developed by Mendeleev. This is way back in chapter 1, I think, or chapter 2. But how long ago was that? That was quite some time ago. Mendeleev's periodic table. And Mendeleev didn't know any quantum mechanics because his periodic table preceded quantum mechanics, but it had the same organization. And the same organization is because he grouped everything into families. The families will have similar chemical properties, like the halogens. You always expect the halogens to gain 1 electron, or get oxide, etc. Or the alkali metals, you expect the alkali metals to lose an electron, etc. And then the properties gradually change they gradually change from metallic properties over here on the left to non-metallic properties over on the right. And so it turns out that the most non-metallic element would be at the top right. And the most metallic element is at the top left. So cesium, francium, those are the most metallic elements. Metals are defined as things, elements that want to lose electrons when undergoing chemical reactions. They also have good electrical and thermal conductivity, etc. Non-metals, there's no one set of properties or one definition that fits all non-metals. Some metals are non-metal gases, some are solids, some are liquids. Actually, not some, one is a liquid. So we can figure out the electron configurations just based on the periodic table. So we have something like, did we do the electron configuration for uranium? Let's take a look at that. Uranium is going to fill up the first, the second, the third, the fourth, the fifth, the sixth. Actually, uranium is element number 92. And so rather than writing it from the very beginning, what we can do is we can work backwards and say we're going to fill up, how many shells are we going to fill up for uranium? Actually, uranium is in the seventh shell. This is the seventh shell is when you just count from the top, 1, 2, 3, 4, 5, 6, 7. Uranium's in the seventh shell because what it does is it goes from 87, 88, and then 89, the actinium, to 90, 91, 92. So it partially fills the seventh shell. And so the nearest filled shell will be the sixth shell. If we fill up the sixth shell consists of the 6s2, and then the 4f14, right here gets inserted, and then the 5d10, and the 6p6, and then we're at radon. So radon fills up the first 6 shells. And so what we can do is we can use the noble gas core, radon, and then we're going to use the periodic table to figure this out. There are different ways we could try to figure it out. We could use the pyramid and see. But after radon's 86 electrons. Where does the 87th electron go? Yeah, that'd be francium. And so that would be 7s1, and then the 88th electron would be 7s2. And so here we're at radium. And then the 89th would be where? Now this is tricky because I said the F are going to fill with how many electrons? There's 7 orbitals, so it should fill with 14 electrons. And so let's count them here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Why are there 15 electrons in F? You can't have 15 electrons in 7 orbitals, can you? That's because there are 2 versions of this periodic table. If you look at this version and compare it to this version, where's actinium in this one? Number 89 is here. And let's count the F. If we count the F, we're at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 14. You expect 14 electrons in 7 orbitals. There's 7 f orbitals. It would be plus 3, minus 2, minus 1, 0, 1, 2, 3. But here, actinium goes in here. This is not the F. This is actually the D. It goes 3D, 4D, 5D, 6D. It's actually on the 6D. So number 89 is out of place. Number 89 actually begins in this. This is an empty box. It says lanthanum to lutetia. Actually here, actinium to lawrencium. So it's going to be 7s2, and then it's going to go 6d1. Now, what happens to the orbital spacings as we get higher and higher in energy? Do the orbitals get further and further spaced apart, or do they kind of converge closer and closer together? they get closer and closer together, and so there isn't a big jump between D and F in terms of energy. And so here, one electron gets kind of stuck in the 6D, and it turns out that the next electron is going to go where? Into the 5F. And so we'll go 5F, and then we're going to fill this whole thing up with 14 electrons. So we're going to start from thorium and N on 103. And so that'll be 5F14. And so once we go to 103, oh, actually, we're not going all the way to 103. We're stopping at 92, which is how many Fs? 4. Is it really 4? You have to watch out because it's actually not 4. It's actually 3. 1, 2, 3, because actinium actually belongs up there. And so it's going to be 5F3. Now, it depends on which version of the periodic table you have. It would have been easier to do it on this version of the periodic table because if we do this, if I want something more complicated, I go backwards. So I start on uranium. This is 92, which is the nearest noble gas. The nearest noble gas would be radon at 86. Okay, so I'll start with radon, 86. Then go to 87 francium, 88 radon, 89 actinium. So it goes 6s2, 5d1, 4, what is that, 5f, 1, 2, 3. And so that would have given us 6. And so we could use the periodic table to figure out the filling for these as well. And so this is why I say, what is the theory of chemistry? Well, the theory of chemistry, we use the periodic table to understand the properties of the elements here. And the theory that underlies this, that is the fundamental description of the organizational structure, well, there are two approaches. One, you could have done it experimentally, from empirical observations, or two, you could do it theoretically. And in theory, we get the same thing, and that theory is called what is the theory called? So the theory of chemistry is the theory that would describe the behavior and properties of the elements here. So this theory would be called, quantum mechanics. Quantum mechanics is the theory that underlies chemistry. It would be great to use quantum mechanics to make predictions of everything, but sometimes that's too much. So for example, if you want the melting point of cesium, would you use quantum mechanics to calculate it? You should be able to. The calculation would be very difficult. So when I look up the melting point in Wikipedia, is the melting point given there the experimental melting point or the theoretical melting point from quantum mechanics? Experimental. Probably the theoretical because the math is so difficult. Wouldn't be terribly pinpoint accurate. Terribly accurate. Anyway, that's chapter 8. We're going to move on to chapter 9. Chapter 9 is the periodic table, part 2. This is an interesting image. These little peaks here are iron atoms. And these little spheres here are copper atoms. Copper atoms are spherical, but are iron atoms cone shaped? What do you think? Do they have a cone shape, or are they round, or what are they? What do you think iron atoms are? They should be spherical as well. It's just the signal. This is the signal that they get, and so this probe is not terribly. I mean, it doesn't have ultra high precision to resolve that. It just sees a signal. That's the atom. And they can move these atoms around. Here it looks much more spherical. But these are all what we call potentials. If who came up with the first meaningful atomic theory? There's some big names like Mendeleev. Mendeleev was the periodic table. And then atomic theory is usually attributed to who? Dalton. Yeah. If Dalton had this, a scanning tunneling microscope, STM, then it would have been pretty easy to prove atoms because with this you could actually see the atoms. You don't see them with your eyes, you can see them with the instrument here. And manipulate them. Then you can try to break them apart using atom smashers, but they don't break into little atoms, they break into subatomic particles. And so this would have been overwhelming proof for the existence of atoms. Here is Mendeleev periodic table. This is periodic properties, so you can range things. This is atomic volume, kind of like density. Less dense elements here. The alkali metals aren't very dense. Gold is much, much more dense. Metals have widely varying density. Francium is not here. Francium has actually disappeared. There's no dot here because francium doesn't last long enough to make like a solid and then measure it. There's something called the half-life. Let's see how long the half-life is for francium. 22 minutes. An intensely radioactive metal, francium has no uses, having a half-life of only 22 minutes. It's difficult to do anything. You can make it. It's made by nuclear reactions, other things, but once you have it, it's like taking time on. It's going to go away. So there's no good data. A lot of these elements that they can't take very good measurements for, they can't get decent precision. So if you look at francium, what's the molar mass of francium? 223, it's in parentheses there because it's not very precise. A lot of these radioactive ones will have imprecise molar masses. Polonium 209, radon 222, all in parentheses. Uranium's got some good data. Uranium, the half-life of uranium is quite long, like billions of years. And so people don't worry about uranium. Whereas if it decayed as fast as francium, you wouldn't have to worry so much. Eventually, uranium would decay to lead. I saw something about uranium is very dense, and so they use it in like projectiles. So I saw something where they had like these bullets made out of uranium rather than lead. You know, most bullets are made out of lead. Lead is very dense also, but not as dense as uranium. But these ones are radioactive. Just scanning YouTube, and they had a Geiger counter measuring the radioactivity of these. We call it depleted uranium. It's not really depleted. The half-life is so long, you know? But if the activity of it gets down to a certain level, then it's depleted enough. So francium's missing. They shouldn't have, they should have had some kind of dashed line with a question mark and then comes down. But what would we predict based on periodic properties? Mendeleev, this is how he generated the periodic table. He would have predicted that francium would be at the highest. Right? And so what probably would have predicted lithium, sodium, potassium, rubidium, cesium, francium. A nice family of alpine metals. Not just atomic volume, but there are other properties too. Melting point. Now, when we look at the melting points, it follows the same trend. Cesium has the lowest melting point. Now, francium should be lower, but hard to take any measurements of that. So cesium melts around room temperature, just slightly above room temperature. So it's almost a liquid at room temperature. Sodium melts around 100 degrees C, and there's a nice gradual change in the melting point as well. There were some elements that were missing out of Mendeleev's periodic table that he, based on the properties, he was able to see the trends in the properties and predicted the properties of these missing elements. I think of those as what, germanium? Here are the melting points. Cesium melts just slightly above room temperature, 28.5. Sodium's at about 100 degrees C. Lithium's at 174. This was gallium, yeah. Periodic table, 1871 version of the periodic table was missing gallium, scandium, germanium. These are all discovered later. This is 1871. Germanium. There's Moseley, but we're going to skip Moseley. A lot of these elements, and this is getting more into the quantum mechanics, will have this, where you blast X-rays. When you blast X-rays, what do X-rays do to atoms? They ionize. And depending on the electrons that are ionized, for example, you can ionize 1s versus a 3s. Which one do you think is harder to ionize, 1s or 3s? 1s, so that's going to be a high energy line in the spectrum. Do you think all the 1s's, like for example, the 1s of copper is going to be the same energy as the 1s of nickel? No, they're going to be different energies because they're going to have a different Z. And so each of these elements gives what we call a fingerprint. There's an energy scale here. And based on the fingerprint, that is, what electrons you ionize and how much energy that costs, like a P versus an S, etc. You can generate this. This is a photoelectron spectrum. You shine photons of X-rays and eject electrons. This is Moseley's X-ray spectra. Not only that, you can identify the elements. Because this is quantitative. The intensity depends on how many photons were absorbed. The more photons that are absorbed, the greater the intensity of absorption. So you can figure. And so something like this if you have a mixture, brass consists of mostly, it looks like brass consists mostly of what? Doesn't quite match up. Brass consists mostly of what copper looks like. Do you see that? Now, brass is a mixture, and then there's some other element that's giving this line here. But we need to match it up here. I don't see a match here. Why are they lined up like that? It's lined up based on energy. And so the energy would be here on the X scale. And then it's short like this because back in the old days they just had film that they used. So they expose photographic film and then see how many photons strike that photographic film there. And then they just place it on different parts of something that can separate the energies, in other words. You can see. And so these are only small windows of the entire spectrum. It'd be better if they showed the whole spectrum, then you could see. But this is old, 1913. So they brought one of these to the moon, you know, more modern version of this. And then what they did was they did elemental analysis of rocks using XPS. In fact, that's one of the topics in our textbook. I actually looked it up earlier. So this is more of what the spectrum, you know, that's using photographic films, but now you have detectors. And so the detectors can detect the intensity as a peak. And so these are the lines, you know, that you saw in the photographic film, but this gives more information here because, you know, in the old days, they have to look at the film and then determine the intensity by how bright that line is there. Or how wide it is. Width it also has important implications too, but rather than just taking a film image, you know, having a spectrum like this is much better. And then you can see here, this is binding energy. And binding energy goes down, increases this way. So the s electrons, the innermost x, like the 1s electron will be here. 1s electrons, there are only 2 electrons, so it'll give you a small peak compared to p. You know, you have the 2s, well, this is quantitative. This might be a 2p here, you know, because it's a much larger peak, more electrons, not off. Figure it out. But here, this is a mixture, and so here we see some 2s electrons being knocked off here, and then 2p electrons being knocked off there for phosphate and phosphide, some elements here. This is the XPS spectrum, some lunar sample. When I was doing X-rays, I used photographic film, and I had to develop it, you know, like in a dark room. And then they had little devices which try to help you measure the intensity, since it's hard to eyeball it. But anyway. So this is just talking about the family. Some of the noble gas electron configuration. The alkali metals +1, alkaline earths +2. Pseudo-noble gas, the critical ones for pseudo-noble gas are like copper, silver, zinc. And then there's something called 18 + 2. And others. We'll talk about some of these. But this is all stuff we've been talking about. So we're going to start here. One of the things we want to look at are the size of atoms. So when we look at the periodic table, this is going to be a sketch of the periodic table here. Where are the smallest atoms and where are the biggest atoms located? Are the biggest atoms located near the top or near the bottom of the periodic table? At the bottom. Okay, are they going to be at the bottom left or the bottom right? Yeah, the bottom left. And so the biggest atom on the periodic table should be francium, but francium is so radioactive, its half-life is only 22 minutes. It's not going to last long, so most people will just say cesium. Cesium's the biggest, if we ignore francium. What's the smallest? Helium's the smallest. And so usually cesium's attributed to the biggest and then helium. Cesium or francium. We'd expect francium to be even bigger than, because that's going to have a whole another shell. Francium should be in the 7th shell. Cesium's the 6th. All right, so first thing, this is atomic size. Atomic size is usually measured by the radius. So how big is the radius? So let's call it atomic radius. What happens as we go left to right? So if we go from cesium, the next one would be barium. Barium is to the right. Is it smaller, bigger? What is it? It's smaller. So cesium, barium. In fact, it should continue to get smaller until we hit radon. Radon should be the smallest over here. Why do they get smaller? Because shouldn't they get bigger? You're adding another electron. Each time you go to the right, we get one more electron. So cesium's at 6s1, barium 6s2. So if barium is 6s2, why isn't it bigger? It has an extra electron. Yeah. It also gains an extra proton. And so what that means is this. It means that Z is getting bigger. And the same thing happens with hydrogen. Hydrogen is bigger than helium. Why? Because helium has 2 protons, hydrogen has 1 proton. 2 protons can pull the electron much closer. Well, this has an extra proton, but it also has an extra electron. Shouldn't that extra electron shield the extra proton? So cesium has how many protons? 87, maybe, no, 55? 55 protons? 55 protons and 55 electrons. Barium has 56 protons, but it also has 56 electrons, so it has 1 extra electron. And the reason is because that extra electron goes in the same shell. And so what we say is this: as we go left to right, Z effective increases. Because Z increases, and same shell electrons are not effective shielders. Inner shell electrons or inner electrons are effective shielders, but same shell aren't. And there's something called Slater's rule. Did I talk about Slater's rules? Let's take a look at Slater's rule. So this is Slater's rule here. Slater's rule is Z effective is equal to Z minus the shielding. not all electrons shield effectively. So what's shown here in this figure are same shell electrons. Are same shell electrons very effective? They aren't very effective because if you have this electron here and it's looking at the nucleus, then what has to happen is this other electron has to block it or shield it. But the probability of it isn't as high as an inner shell electron. If we look at the inner shell or the core electrons, they're inside here. So core electrons are very effective shielders. However, same shell electrons aren't very effective shielders. So this is for aluminum here. Aluminum has 10 core electrons and 3 valence electrons. The 10 core electrons here are going to shield very effectively because those would consist of the 1s, the 2s, and the 2p. When you add up the entire shell, 2s and 2p, it's spherical in symmetry. So that's why we just draw one big ball there. And so we have 13 protons and the 10 core electrons. The 10 core electrons are going to block 1 for 1. They're very effective shielders. So the net charge becomes +3. And so we start off with 13. We lose 10 because of the core. Now, that +3 is going to drop down because of these other electrons here. So we have 2 more electrons, let's say, blocking this one. And so it's not going to go down to +1 because these are much less effective shielders. Well, how much does it go down by? And that's what Slater came up with. Slater came up with different levels of shielding. So realistic values of Z effective can be obtained from analysis of wave functions. Yes, if we want to do the quantum mechanics, but the quantum mechanical calculations aren't easy. We don't have a computer with Spartan or something like that. So we're going to just do these qualitatively by hand. The qualitatively by hand is like this. And these are some simple rules that Slater came up with. Okay, let's say we're looking at the 3s and the 3p, the third shell electrons. If we're looking at the third shell electrons here, 3s and 3p, how effective are the 1s electrons from blocking those? So if you look at where the 1s, this is the radial distribution of the radial probability function. The most probable location for the electrons is here. And so the most probable the most probable distance from the nucleus is here, then the 1s electrons are very effective at shielding the 3s and the 3p electrons from the nucleus. Can you see that? If we just move this one up here, it's going to block it very well. And so we say that the 1s electrons will shield with 100% probability the nucleus. All right, so we're looking at aluminum. Aluminum has 3 electrons up here, 2 electrons in 3s and 1 electron in the 3p, the black. 3s is the purple. And it has 13 protons, which means plus 13. We have 2 electrons in 1s, those are going to completely block 2 of the 13. So if we completely block 2 of the 13, then we're at plus 11. Okay, what about the 2s and the 2p? The second shell. Are the second shell going to be as effective as the first shell? No. In fact, we have to look at the n-1 shell. Because if we're at the fourth shell, the fourth shell would be way out here. Would the 2s be effective? Yes. The 2s would be very effective. So if we're at the fourth shell, which is pretty far from the nucleus compared to the third, if we're looking at the n equals 4, except for the 3D, the 3D are closer. I shouldn't say fourth shell, I should say if we're looking at n equals 4. N equals 4 is 16 times the distance. N equals 3 is 9 times the distance. N equals 2 is 4 times the distance. N equals 1 is the distance, let's say. The reference distance. So this is what we say. If we're looking at shielding from the shell below or the whatever, shells is very tricky, so I use that term very loosely. If we're looking at the shell below, then it's 85%. And so the 1s would be 100%, and then the second shell would be 85%. And so we have 8 electrons in the second shell, and we're not going to lose 8 positive charges. We lose 0.85 times 8. .8 positive charges. So Z effective is equal to Z13 minus S. Okay, so the 1s electrons completely shield. And then the n minus 1 electrons, 2s, 2p, which would be n minus 1, are going to shield at 85%. Then we have 8 electrons. And that's going to be minus 6.8. So far we have 13 minus 2 minus 6.8. And then we have the same shell electrons. Same shell electrons, we're going to have a total of 3 electrons. And same shell electrons aren't very effective shielders. So if we're looking at this as the same shell electron, we're going to have 2 electrons, and it's only going to be about 33%. And so 0.33 times 2 is 0.66. And so we get 13 minus 2 minus 6.8 minus 0.66. .54. That's an estimate. So just say about 3.54 is the effective. And so by using these rules here, the Slater's rule, we can figure out, about what the effective should be. There it is. Roughly speaking, valence electrons are no more than 1/3 effective in screening. And so the 3 levels would be 100% effective, 85% effective, 33% effective. Depending on how many shells. If we have multiple inner shells, then we're going to get, we can use Slater's rules. Determine this. You aren't going to have to do any calculations with shielding and screening. We'll skip these here. So we see this pattern repeated here. These are same shell electrons. Same shell electrons only about 33% at the most effective at shielding. And so essentially, as we go across here, Z goes up and Z effective goes up because those same shell electrons aren't so effective. And what's going to happen to the size? If we go from rubidium, the biggest, down to what would be the smallest in this period, not iodine, what would be smaller than iodine? There's one element missing. And so we go from rubidium to xenon. Xenon should be the smallest. And so rubidium to xenons. Rubidium the biggest, xenons the smallest. And the size shrinks because Z effective is going up. You see it here, the size is shrinking, although there's some weird stuff going on here. But from sodium to chlorine, shrinking. From lithium to fluorine, it's shrinking. Z effective is going up. Essentially because same shell electrons are not effective shielders. All right, what about when we go from cesium to rubidium? What happens to the size? Well, Z is going down. Cesium has a Z of 55, rubidium has a Z of 37. So that means rubidium should be bigger, right? Rubidium should be a lot bigger because Z is a lot smaller. Is that correct? No. Actually, rubidium turns out to be smaller than cesium. And so let's look at it from the other way. Why is cesium bigger than rubidium? Because there's an extra shell. There's an extra shell, and the extra shell is going to result in very effective shielding. In other words, we'll have another filled shell, which we'll call a core shell. And Z effective is going to be roughly the same. A little higher, but roughly the same. So the size decreases going up, and the size decreases going right. And so I should write here, the radius decreases. As we go up, the radius decreases, but the reason's different. Z effective is relatively constant, a slight change, but we have shells. We lose a shell. We'll call it end shell. Or we grow in size as we go down. And so the size trend goes like this. Size increases as we go down and to the left. And size increases as we go up. Size increases, as we go down and to the left. Size decreases as we go up and to the right. All right, the next thing we're going to take a look at is ionization energy. Ionization energy follows a periodic pattern or trend. I'm going to abbreviate ionization energy IE, or ionization energy. Your book uses E sub I, meaning energy of ionization. We just use IE. Ionization energy is we take an atom of gas, gaseous atom here, and just strip an electron off to make a gaseous cation. This is what we'll call IE1. Okay, IE1, and then there's 2, 3, etc. Go down. And so an example of that is some things want to lose more than one electron. Aluminum. So if we take aluminum, it has to be gas. Normally aluminum is a solid, so what we have to do is melt it and then vaporize it. Well, actually, we have to heat it up to its melting point, melt it into a liquid, and then heat the liquid up to its boiling point and then vaporize it. And so we'd use Hess's law and add up all that energy. Eventually, we'll get it in the gaseous state. Once we get aluminum in the gaseous state, then we'll hit it with IE1, either with an oxidizer or a photon. And then IE1 will take us to aluminum plus 1, plus an electron in the gaseous state. And then we'll hit it again with IE2, which will take us to aluminum 2 plus 2 electrons, to keep things balanced. And then IE3, which will take us to aluminum 3 plus a total of 3 electrons, to keep things balanced. These are called successive ionization energies. So if I want to ionize aluminum, what I do is I add these up using Hess's law. Hess's law, we used to add things up. The individual steps make up the overall reaction. So when we look at the ionization energy, what's easier to ionize, cesium or helium? Cesium. Cesium is going to be a lot easier to ionize. If you're an oxidizer, you can probably take an electron easily from cesium, but you're going to have a hard time from helium. And so ionization energy follows the exact same trend as size, because the smaller atoms are harder to ionize, and the bigger atoms are easier to ionize. And so what we're going to see for ionization energy is this pattern. As we go up and to the right, the ionization energy increases, increasing ionization energy. And follows the size pattern. This is for IE1. We're just going to look at the first ionization energy, and we're going to compare the first ionization energies just to get a fair comparison. You know, which element is easiest to ionize? Well, some elements you want to ionize not once, but twice, or even 3 times. Others only once. And so if we look at IE1, let's start off with lithium versus beryllium. Which one is going to be easier to ionize? The bigger lithium or the smaller beryllium? Lithium's easier to ionize. Which one is going to have a higher ionization energy? One. Yeah. Beryllium. So beryllium is going to be harder to ionize because it's smaller. That's what we expect. And then we go to boron. Boron is smaller, so it should be harder to ionize. And so IE1 for boron should be greater than IE1 for beryllium. That's what we expect. And then we go from boron to carbon, and then carbon to nitrogen. And it just keeps getting smaller. Nitrogen to oxygen, oxygen to fluorine, and fluorine to, actually this is over exaggerated, it doesn't shrink down that much, but they go to neon. About how much does it shrink down? Let's see. Get a rough idea. Close the page. Shoot. sent a closed page here. Let me just pull up. Well, we'll take a look at it in a minute. About how much smaller does it get? This one was too much, but over-exaggerated, but this is what we expect. However, there are two blips in this, and that is here. Boron should have a higher ionization energy than beryllium, but it doesn't. It actually ends up that the ionization energy for boron is actually less than the ionization energy of beryllium. The other blip comes here with oxygen. For oxygen, the ionization energy is actually less than the ionization energy for nitrogen. And so from nitrogen to oxygen, we have an exception, and beryllium to boron. There's another problem here. These are significant. We can see it in the graph of ionization energies here. Hydrogen to helium works fine. Helium is going to be higher. Here we go, lithium to beryllium. Beryllium is smaller, ionization energy is greater. But when we go from beryllium to boron, boron's ionization energy is less than beryllium, or is expected to be greater. Can you think of a reason why boron would actually have a lower ionization energy when it's smaller?
Well, one thing that would stand out is from beryllium to boron, you're going from the 2s to the 2p. So maybe just only one electron, the 2p is kind of easier to take than
Yeah.
the 2s.
So that's the reason why. A 2p electron is easier to ionize than a 2s. And so this is attributed to a 2p electron versus a 2s electron. Yeah. Okay, once we're ionizing 2p's, then it's all relative to that. And so carbon's smaller, and we're ionizing a 2p, and so it's going to be harder to ionize. Nitrogen's smaller than carbon, it's harder to ionize. But when we go from carbon to oxygen, oxygen turns out to be easier to ionize. Why is that?
I just asked the question of, you said we're facing the size of atoms, but is the bigger atom easier to ionize or not?
Easier to ionize. Bigger atoms are easier to ionize because bigger atoms, the electron's further away from the nucleus. And so it's easier to take. So oxygen's smaller, but why should it be easier to ionize than the bigger nitrogen?
Is it because nitrogen has a half-filled shell or half-filled P?
Yeah, nitrogen has a half-filled P. So when we look at the valence, we'll just do the valence here. Or we could do the whole thing. And then the whole thing's pretty easy because this is one S. So in nitrogen, we're taking one of these electrons here and stripping it away. Whereas in oxygen, its energy level diagram is going to look a little bit different. How so? Yeah. We're going to have one extra 2p. And where does that one extra 2p go? Into one of these three. We'll just pick the first one. And which electron should be the easiest to ionize? Would it be the paired electron or the unpaired electron? It turns out the paired electron is the easiest to ionize. The reason the paired electron is easiest to ionize, and this is what it's attributed to, it has a little push, it has a little extra help. The extra help comes from what we call electron-electron repulsion. Both electrons are negatively charged. Like charges repel. And so electron-electron repulsion is due to the minus being repelled by the minus. And so both of those electrons are in a 2p orbital. Is a 2p orbital? 2p orbitals are small. And so the electrons are crowded, in a sense, and therefore electron-electron repulsions can be significant. So here, nitrogen is harder than oxygen. Oxygen is unusually easy because of the electron-electron repulsion is helping to ionize it. But once we get from oxygen to fluorine, then it doesn't really matter, you know, because fluorine's going to have just one more paired one here. Use that. And finally, we're going to end up in neon with all the electrons paired, but it's going to be difficult to ionize because it's such a small atom. All right, so one of the things is you notice a significant drop in energy here. That means the pairing must be more significant than there. If you look at this, was there a very significant drop here? No. And the reason is because we aren't dealing with 2p orbitals. We're dealing with 3p orbitals. 3p orbitals are a lot bigger. If 3p orbitals are a lot bigger, then there's lots of room to accommodate the electron. Having lots of room to accommodate the electron, the repulsions aren't going to be as significant. And so the repulsions aren't as significant here. And so we see this pattern here with heat. Here we're ionizing a 3s. Here we're ionizing a 3p. And so the first drop. Here we're ionizing an unpaired p. Here we're ionizing a paired p. And so that accounts for these two flips. There are some other stuff going on here. What a good theory should be able to do is, you know, good theory should be able to describe this in terms of some fundamental picture of what's going on. So that's what we're trying to do. We're not going to try to explain all the blips here. So why does this shoot up here and then stabilize again and go up and drop? Here it's much more significant. Well, actually, it's insignificant here. Here's the S and here's the P. And so in fact, there was no drop there. The S and the P aren't that different than what's going on there. And so those are things that a theoretician would look at more detail, try to figure out. But those are the ionization energies. And so we look at what species have the highest ionization energy, the smallest. What species are the smallest? The ones on the right side of the periodic table. And so we see on the dashed line here all of the elements on the right side of the periodic table, starting off with the smallest, helium, neon, argon, krypton, xenon, radon, all the noble gases. The noble gases are very difficult to ionize, with helium being the hardest. And if we look at the ionization energy is in kilojoules per mole, so it's almost at 2,500 kilojoules per mole. We'll just say it's about 2,500 kilojoules per mole. That's going to make these very difficult to ionize, which means they're going to be quite unreactive. So the noble gases are quite stable, hard to ionize. Whereas the alkali metals are very easy to ionize. Well, very easy in the sense that it requires a lot less energy. So the ionized alkali metals cost around 500 kilojoules per mole. Which alkali metal is the easiest to ionize, it looks like? It should be francium, but it looks like francium and cesium are about a tie there. So, for the factors going on, but the biggest ones there. And francium is a bit below 500. These are very reactive because these are easier to ionize. So an oxidizer comes along, it doesn't work too hard to pull an electron out. And so what we should know is the range, you know. Hard to ionize around 2,500 helium. Easy to ionize around 500. It's sodium, lithium. There are other patterns here. You know, this is pattern. We're not going to talk about this one, but this one made Nature magazine. Nature magazine's must be significant. And so let's take a look at some ionization energies. So we would see the same pattern. This is the second period. In the third period, we start off with sodium, and we'd end with argon. And we'd see the same two blips, so it followed the exact same pattern as this. All right, the next thing we're going to look at is electron affinity. So ionization energy, actually, there's another thing I need to talk about. Ionization. This is only for the first ionization energy. That's not for the alkaline metals, but the alkaline earth metals, they want to lose 2 electrons. So I need to look at one more figure for ionization energy. Here it is. So this is showing the alkaline metals. The alkaline metals are easy to ionize. You know, the hardest of the alkaline metals will be lithium, 520 kilojoules per mole. Cesium would be very easy, 375.7 kilojoules per mole. But they're all fairly low. These are what we call low. So sodium is fairly low ionization energy, about 500. Magnesium is smaller. So magnesium would have a higher ionization energy, 737.7. Then aluminum is smaller, but when you look at aluminum is smaller, but its ionization energy is not bigger like we'd expect. If it's smaller, it should be bigger. But it's smaller, and the ionization energy is smaller. So that's a bit unusual. Why was that? Yeah. Here, this is the difference between 3s and a 3p. 3p being less penetrating, easier to ionize. But now we're ionizing 3p, so silicon's smaller, so it has a greater ionization energy, i.e. 1. And then phosphorus is smaller, greater ionization energy, 1012. And then sulfur is smaller, so we'd expect a greater ionization energy, but the ionization energy turns out to be less. Why is that? We call it electron-electron repulsion. And then it follows the pattern. The next pattern that we're going to look at are successive ionization energies. So IE1 for sodium is 500, but IE2 for sodium is 4,500. So it's about 10 times more energy. But when we go to magnesium, IE1 for magnesium is 738. IE2 for magnesium is only 1,400, so it doesn't go up tenfold. If it went up tenfold, it'd be 7,000. But when we go to the third ionization energy, it is now 7,000. And so do you see the pattern here? The pattern is this. When we try to ionize what we call a core electron, the ionization energy show a dramatic jump. However, when we're ionizing valence electrons, the ionization energy does significantly increase, but not nearly as much as core. And so magnesium has 2 valence electrons. The first one's 738, the second one's 1400. If we want to ionize both to form magnesium 2+, then we have to add these together by Hess's law. And so ionizing 2 electrons off of magnesium is going to be out 20 over 2,000, 2,100, 2,200. But ionizing the third one, significant cost. Aluminum has 3 valence electrons. The first one, the second one's about triple here. The third one's about double the previous. And so it looks like, successive ionization energies of valence electrons goes up by what? By about 1,000 kilojoules per mole each step. And then a significant jump here. And so what this chart's showing that the core electrons are very difficult to ionize. And the valence electrons are reasonable, but they can add up. So if you tried to form phosphorus plus 5 would be its max positive. It would cost you 1,000 plus 2,000, 3,000 plus 3,000, 6,000 plus 6,000 plus 5,000 would be 11,000. It would cost you about 17,000 kilojoules to go to P plus 5, which is huge. So successive ionization energies grow, and then when we get to core, a big jump. So those were the ionization energies. The next thing we're going to look at is electron affinities. Electron affinities are kind of the opposite process. So ionization is removing, electron affinity is gaining. And so if I take a gaseous atom and add an electron to it, I'll make an anion in this case, rather than a cation. And the energy that's involved here is called EA, electron affinity 1. Likewise, we can have electron affinity 2, 3, etc. So electron affinity 2 would be taking that gaseous anion, A minus gaseous state, plus an electron, which would give us A2 minus in the gaseous state. That would be EA2. So the situation is this. What's the difference between electron affinity versus electronegativity? Do you know what the most electronegative element is on the periodic table? Fluorine. Fluorine is the most electronegative element on the periodic table. And so shouldn't that also have the highest electron affinity? Affinity is the love of electrons. So fluorine would be it. And so we'd expect fluorine to have the highest electron affinity. And it should, but it doesn't. And the reason it doesn't is because they're looking at one additional thing. The ability to accommodate an extra electron. Electronegativity is the ability to attract an electron, but not necessarily accommodate it. Where are you going to put that extra electron? In the case of fluorine, if fluorine gains an extra electron, so fluorine's going to have the strongest attraction. So if we take a gaseous atom, so this will be atomic fluorine, not diatomic, so we'd have to break the bond. And then we give it an electron, we'd form fluoride. Well, fluoride's very stable. Does chlorine have lower or higher electronegativity? Chlorine has lower electronegativity. Fluorine has a higher electronegativity. But do you know which element has the highest electron affinity on the periodic table? It turns out chlorine has a higher electron affinity than fluorine. So when we compare the two electron affinities, we expect fluorine to have the greater electron affinity. But what's observed is the opposite. This is the only weird exception. And so why is that? Why would chlorine have a higher electron affinity when it has a lower electronegativity? That's weird. Can you think of a reason why? The reason why is because fluorine has a greater ability to attract an electron. So it pulls an electron, it's a great oxidizer, it's the most powerful oxidizer. But once it gains that extra electron, where does the extra electron go? Into what orbital? It goes into 2p. Are 2p orbitals big or kind of small? 2p compared to 3p. So they're small. And so what happens is we get crowding. So that extra electron has to pair up with another electron in the 2p orbital. And it's not quite as accommodating. Whereas chlorine doesn't have a big pull for electrons, but if it does take an electron, chlorine's a decent oxidizer. If it does take an electron, that electron goes into its p orbital. But the big difference here is it's going into a 3p orbital versus a 2p orbital. And so this is 2p, this is 3p. 3p orbitals are going to have less electron-electron repulsion than a 2p orbital. And so a 3p orbital is going to be a more stable place for that extra electron than a 2p orbital. And so it turns out that chlorine has the highest electron affinity on the chart. So let's take a look at electron affinities. Electron affinities are negative here. So if we look at the electron affinity for fluorine, its electron affinity is minus 328 kilojoules. Minus 328 kilojoules. Whereas for chlorine, it's minus 349 kilojoules. So when we say it has the highest, that means it's going to be the most negative, that is 349. In other words, it's going to be stabilized by 349 kilojoules. So what we're looking at with chlorine is going to go into a potential well. We call it a potential well because it's low energy. And the potential well is going to be 349 kilojoules deep. And so it'll be down here. And we can think of it in terms of like gravity. You know, if you don't like heights, then you want to be low. And the lower you are, the less you're going to fall. So this is going to be quite low. It's going to be lower than this. And being lower is going to be more stable. Therefore, it's more favorable. And therefore, chlorine has the highest electron affinity. Minus 349 kilojoules is the highest electron affinity. But that's kind of in the upside down of potential wells, you know. You don't want to be too high. You want to be down low. Some people don't like that. So when somebody says which has a higher electron affinity and you give them two numbers, which one is a higher number? Minus 328 or minus 349? Some people might get confused. Since some people might get confused, your book does this. Your book will plot it like this. Which one has the highest electron affinity? Chlorine, although it looks like fluorine, but it's not fluorine because you're looking at an angle. Chlorine has the highest electron affinity. And so what they're doing is they're just inverting all the potential wells. And so this has the deepest well. In other words, what they're doing is they're taking the negative of the electron affinity here. Can you see that? I don't like to do that. To just multiply by negative. And so which one has the highest negative electron affinity? It would be chlorine. Which one has the highest electron affinity? Well, your book would say, well, it wouldn't be this because it's, I don't like it. So anyway, this is it. Most stable. Now, we're almost out of time, so anyway, these are going to result in stability. And so I'll just stop here. We're getting it. We're going to finish up chapter 9 Monday. And then 10 and 11 we're doing with lab. Or actually Tuesday we'll finish up chapter 9. And then with lab I think I'll get caught up again. So I'm a little behind.